Okay, the topic of today is lecture 5. It will be about integration. We will view integration as anti-differentiation, and later on I will just motivate the interpretation that one has for integration. Just now we considered it merely as anti-differentiation. The material can be found in sections 2.10, 5.3, up to 5.6 and 6.1 of the book. Okay, now the main theorem that we will use for integration, or at least which is at the core of integration, is the theorem in section 5.5, theorem 5, which is called the fundamental theorem of calculus. And I will reformulate it slightly differently than in the book, but of course it will mean the same thing. Now, we suppose that we have a piecewise continuous function, little f. So it's defined on some interval, capital I. Now you know what a continuous function is, but piecewise means that it is composed of a number of continuous pieces. You can find the precise definition in the book. We have seen piecewise continuous functions already with distribution function associated with the coin tossing problem. We have this right continuous function which makes jumps, and so we have piecewise continuous parts of this function which are paced together. Now, what can we say about such a function? Well, there exists a function capital F such that the derivative of capital F is equal to our little f. This function has a name. F is called a primitive of little f. And we have of course also some special notation for primitives. We write capital F is equal to the integral over little f dx. Now, since we don't specify the integration interval, we call such an integral an indefinite integral. So the point is that this primitive is not unique, because if we differentiate constants, we get 0. So with taking primitives, we get a whole bunch of these. So in fact, we can get all possible primitives just by adding a constant to our one chosen primitive. Now, if you integrate, you always should add this particular constant, because otherwise you didn't solve the problem. Now, what happens if you take any particular primitive, any one of these for some constants, say c is equal to 3 or whatever you like. So we take one of these, we call it g, capital G, to differentiate from our capital F. Now, primitive capital G means that the derivative of capital G is again our little f. And then we define the definite integral as follows. It is just the integral from 0 to x of our function little f. And since we have x in our integration, we cannot integrate over x, so we choose another integration variable t, and this is equal to the difference between the value of our capital G at x minus the value at a. And such an integral is called a definite integral, as I already said. Okay, so we have defined these functions just by doing anti-differentiation. So we just look for what functions capital F are such that if we differentiate we get our original function back. Now we know, you know already, but as I said before, we're not going to discuss this at this point. We have an interpretation for a function little f if it is non-negative. Then if we sketch this function, so we have, for example, a continuous function little f, so we sketch it, we choose our point A and a point x, and if we calculate the surface under the function little f that we draw, since it's positive, the integral from a to x of our function is precisely the surface of this green area. So this is of course the way how the integral originally was defined, but okay, it's a topic of a later lecture. Now, how do we calculate integrals? This is really a much harder topic than differentiation, and I think the best thing is to say is that you just make a guess and check by differentiation. Of course, we can make educated guesses, so we'll discuss a number of ways to make educated guesses. For instance, the problem with integration is also that we do not always have explicit formulas for primitives. So if you want to compute the primitive of e to the minus x squared here, x, which is basically the density of the normal distribution, which undoubtedly you already saw, then we have no expression available. We simply can't give any function in terms of powers or logarithms or polynomials or goniometric functions, trigonometric functions that combined together would yield the primitive of this function. So we have no expression, and we have to evaluate definite integrals involving this function just by making a table, by numerical approximations. So